realize these problems take a little bit longer and you might not be done, but let's see if you've gone in the right direction so far. So for the first one here, y equals x squared minus 4. So that is a parabola because it's quadratic form, x squared. And instead of being centered at the middle of the graph, it goes down 4. The vertex is right there. And that gives us our parabola. Now it is greater than or equal to, so it is going to be a solid curve. We don't have to do a dashed curve for it. But we do need to figure out where it is shaded. So I'm going to use the origin as clearly inside the parabola. So let's use that as our test point. Is 0 greater than or equal to 0 squared minus 4? Well, 0 squared minus 4 is negative 4. 0 is greater than or equal to negative 4. So that point is true. Since it's on the inside, we shade the inside. Now we'll graph the second one down there. X minus y is greater than 2. Now again, what we're really graphing is we're going to graph the x minus y equals 2. We could put this in our slope-intercept form if we wanted to. We could subtract x from each side, giving us negative y equals 2 minus x, and divide by negative 1, or multiply by negative 1, either one, to get rid of the negative. So y equals negative 2 plus x. So that means it starts at 0, negative 2 is the y-intercept, and it's just a positive x. So it's a positive 1x. You go up 1 over 1 for our slope. Now that is strictly greater than, so it's going to be a dashed line. That one needs to be shaded as well. So again, the origin is obviously above that line. Let's test the origin. 0 minus 0 greater than 2. That is not true. So the side the origin is on is not true, so we have to shade the other side of that line. So our solution is where they overlap. And they overlap down here. So the part that's bordered by the parabola is solid line. The part that's bordered by the line is dashed, and of course it's shaded inside there. So that portion right there is our solution. For the second one over here, any questions on that first one? Okay, so for our second one over here, we're going to graph the top one here. Both of these are in the form of a circle. So the top one, x minus 2, that's going to be positive 2. X plus 1 will be negative 1, so that's our center. R squared equals 16, so that means the radius is 4, so we go 1, 2, 3, 4 this way. 1, 2, 3, 4 that way. 1, 2, 3, 4. 1, 2, 3, 4. That is less than or equal to, so that is a solid curve. The origin is clearly inside. Actually, let's just test our center point here of 2, 1, or 2, negative 1. If I put in 2 and negative 1, I got 0 over here. 0 is less than 16. So that means this one is shaded on the inside of the circle. The second one, x minus 1, that means the center is at positive 1. Y minus 1, that's also positive 1. So right there is our center at 1, 1. R squared equals 9, which tells us that the radius is 3. So we go 1, 2, 3 this way. 1, 2, 3 this way. 1, 2, 3 that way. 1, 2, 3 that way. That is strictly less than. So that's a dashed line. Less than, if I test the center point, if I put in 1, 1, I get 0 plus 0 on this side. That is less than 9. So the center, the inside of this circle, is also shaded. So the overlap here From this circle, this is a solid border. From this circle, it's a dashed border. And of course, we're coloring in the inside of it there. That part is the solution. Any questions? Okay, so now for number 3, we're asked to optimize this objective function over these constraints, under those constraints. This is a linear programming question. So I'm going to write that objective function down here, z equals 2x plus 4y. And we'll come back to that in a little bit. Let's graph our constraints here. 2 of our constraints are x is greater than or equal to 0 and y is greater than or equal to 0, which tells us that we're only working in this first quadrant over here. So that's all we need to worry about. Our third one is x plus 3y is greater than 6, greater than or equal to 6. So I could solve that for y, would give me y is greater than or equal to 2 minus 1/3 x. At this point, I'm going to trust that you guys can solve that for y. So this starts at positive 2, goes down 1 over 3, down 1 over 3. It's greater than or equal to, so if we test the point 0, 0, if I put 0 in there, it is false. 0 is not greater than 6. So it's the other side of it that is shaded. So we're shading the top side of this line. The fourth equation, x plus y equals 3, well, that would be, or x plus y is greater than or equal to 3. If we solve that for y, y is greater than or equal to 3 minus x. So we start here at 3. Minus x means it's a slope of negative 1, so down 1 over 1. So we get that. If I plug in 0, 0, 0 is not greater than 3, so it's not on the side of the origin. So the origin's over here, so we shade the other side. And our final constraint, x plus y is less than 9. So the equation 5 there, if I solve that, I get y is less than or equal to 9 minus x. So I go up here at 9. So it's 3, 4, 5, 6, 7, 8, 9. And slope of negative 1 puts me in an equation like that. It's less than or equal to, so if I put in 0, 0, 0 is less than or equal to 9, so I'm shading that one below the line. So my solution here, or my constrained region, I should say, my allowable solutions, slightly different color so it shows up better, is in this shape right here. So remember, we test the objective function at the vertices, the corners of this constrained region. This point here is 0, 9. That one's easy to come up with. This point here is 0, 3. This one we're going to have to do a little work on. This point here was 6, 0. This point over here is 9, 0. So we need to find this point. This point is the intersection of these two equations right here. So if I set these two pieces equal to each other, 2 minus 1/3 x equals 3 minus x. If I add x to both sides, I get 2 plus 2/3 x equals 3. Subtract 2 from both sides. I get 2/3 x equals 1, and then I'll divide by the 2/3. So x equals 1.5, 3/2. So then I just plug that back into one of the equations. I know in this 1.5 is the first coordinate. I plug that back in. 3 minus 1.5 is also 1.5. So my y-coordinate has to be 1.5 as well. So that point is 1.5, 1.5, or 3/2, 3/2. So I need to test all of those points. I have 1, 2, 3, 4, 5 of them in my objective function. So let's test 0, 9. That'll be 2 times 0 plus 4 times 9. That gives us 36. Let's test 0, 3. That's 2 times 0 plus 4 times 3. That gives me 12. Let's test 1.5, 1.5. 2 times 1.5. Write that correctly. Plus 4 times 1.5. What is that? 3 plus 6 is 9. Let's test 6, 0. So 2 times 6 plus 4 times 0 is 12. And finally, let's test 9, 0. So 2 times 9 plus 4 times 0 is 18. So the point that maximizes that objective function is the point 0, 9, which gives us an objective value of 36. Any questions on that problem? Okay. Any questions off the homework from last week, Wednesday? Okay, so today we're going to shift gears a little bit again, and we're going to talk about a tool. It's going to take us a couple of classes of learning about the tool before we get to the point where we use it for doing things, shortening up some of the processes we've done so far. And the tool we're going to talk about is matrices. A matrix is nothing more than an organized set of numbers. The value of the number is important, but just as important is its position within a matrix. So this here is a matrix. Those square brackets symbolize that what's inside of it is a matrix. Our matrix has rows. This one has 2 rows. And it has columns. The dimensions of a matrix or the dimension of a matrix, I should say, is the number of rows by the number of columns. Now, that doesn't mean we multiply them out. That just means we list them as row by column. So this matrix has 2 rows and 3 columns. It would be called a 2 by 3 matrix. Because the numbers in these matrices are locked in a position, we can use them to represent more complex mathematical constructs and leave out a lot of the stuff that kind of gets in the way. For example, we might have a system of equations (3x minus 2y equals 16) and 2x plus y equals -1. We can represent that, at least we can represent the coefficients with a matrix. We've got 3 and 2 are the coefficients of x. This is -2 and +1 are the coefficients of y. So that's a matrix representing the coefficients of the variables in that system of equations. Now note that we had to have the system of equations in a form so that their coefficients were in the right location. This had to be set up as the x variables, the y variables, the equal sign, and then the constants. If they weren't arranged in that order, we would have to rearrange them before we could represent them in the matrix. Because not only is the position of the numbers in the matrix have meaning, but what we're representing had to be in the proper form so that we could represent it with that matrix. Now, this matrix itself will become useful to us as we go through some of our properties of matrices at some point. But for what we're doing today, we want to go a step further and talk about something called an augmented matrix. In an augmented matrix, there are additional numbers that basically come along for the ride. Anything that we do to the other numbers, we have to do to them, but they don't determine what gets done. They're just kind of tagging along with the other numbers. So for this system of equations, we have our coefficients. This line here represents a separation between the actual matrix and then the augmentation. So the augmentation would be the constants here. So the 3, -2, the 16 goes with them, because that is the constant on that equation. And with the 2 and the 1, the -1 goes with those. So this is a matrix that has been augmented for the constant values of the system. So this is really the matrix itself. This piece in here is the augmentation. Like I said, the 16 and -1 here are along for the ride. Anything we do with the other numbers, we're going to do with them as well, but we don't use the 16 and the -1 in the process of determining what needs to be done. So with a matrix, we are allowed to do what's called row operations. So things that are allowed in a matrix. Number one, you can interchange rows. So with my matrix up above there, the matrix is 3, -2, 16, 2, 1, -1. I could interchange the rows. I could make that 2, 1, -1, 3, -2, 16. I have not changed the meaning of that matrix. If you think about it back to that original system of equations that it represents, all I've done is flipped one equation from the bottom to the top. We are allowed to multiply or divide a whole row by a constant. Remember, we've multiplied whole equations before. Multiplying a row here is that equivalent. So I could take this first row and multiply it by the constant 2. So that first row is going to become 4, 2, -2. And the second row, of course, hasn't changed. There's my new matrix. I just multiplied a row or divided a row by a constant. The third thing we can do is I can add two rows and use the sum to replace one of those two rows. Now here I only have two rows, but I can still do it. I can add these two rows. So I'm gonna do the 4 plus, and I'm gonna replace the top one in this case. So the 4 plus the 3 is 7. 2 plus -2 is 0. -2 plus 16 is 14. So I replace the top row. Even though I use the second row, I'm keeping the second row here. I combine the two, but I only replace one of them with that sum. So the purpose of these row operations, and we've actually started it here, is to get zeros in certain locations. We have what is referred to as a diagonal matrix. In a diagonal matrix, we have desired numbers along the diagonal. And when we're dealing with matrices, there's different forms of this. One form is called row echelon form. Now, row echelon form, depending on what textbook you're using, can look a couple of different ways. Let's say we've got a 3x3 matrix augmented with a set of solutions. So it's essentially a 3x4 matrix. So 1, 2, 3, 4, 5, 6, 7, 8, 9. The augmentation on the other side over here. To be in row echelon form, we need two things to happen. One, we need ones along that diagonal. The second thing that needs to happen is everything below and to the left of those ones has to be a 0. The other locations can have whatever value holds true or works out. Now there's also something called reduced row echelon form. Reduced row echelon form is actually more useful. If you have a graphing calculator, it is one of your matrix options. It's RREF, reduced row echelon form. And in reduced row echelon form, what we have is we still have ones along that diagonal, but now instead of having just zeros to the lower left, we also have zeros above and to the right, but the augmentation can still be whatever number goes with it. The reduced row echelon form is way simpler if you can get the matrix in that form. So let's take a peek at how this works. So I'm going to give you a system of equations. We actually had one up here. Let's go back up to it. 3, -2, 2, 1. So here's our system of equations. Now we've already put this into an augmented matrix. We've seen it. It looks like this. So that is the augmented matrix that corresponds to this system of equations. Now let's put this into row echelon form. Helps if I put all the letters in my word. So that means I need ones in each of those two places. Well, I already have a 1 here. That's good. But I need this to be a 0 as well. Now we actually did this kind of haphazardly as we were showing the row operations that are allowed. We actually had turned this into a 0, which isn't necessarily what we want to do, but it doesn't hurt. So anyway, let's go ahead. We want to turn this into a 0 and we want to turn this into a 1. So the first thing I'm going to do here is I'm going to multiply that bottom equation by a -1. So now we have the matrix, not bottom row, I should say, by -1. Now we have the matrix. The top row is not affected, 3, -2, 16. The bottom row becomes -2, -1, +1. Now I am going to combine the rows and replace the bottom one. Or sorry, I'm going to replace the top one with it. So 3 plus -2 is a 1. -2 plus -1 is a -3. 16 plus 1 is 17. The bottom row I'm just going to leave the same right now. You'll notice at this point I have a 1 there. Now there are a lot of times that we want to multiply a row by a certain number, but we want to keep the original form of the row. Like this top row, I want to multiply it by ×2 right now to get 2, -6, and 34. And the reason I wanted that is because I'm going to come back and I'm going to add those two rows together and replace the bottom row. 2 plus -2 is 0. -6 plus -1 is -7. 34 plus 1 is 35. But I don't want this row to go back up top. I want the row I had before I multiplied it back up top. So technically what I'm doing is I'm dividing that row by 2 again to get it back to this one. So it's just 1, -3, 17. It's what it was before we multiplied. So we're 2/3 of the way there. We have a 1 here, we have a 0 here, but we don't have a 1 here anymore. We've got a -7. So there's two ways of thinking about it. I can divide that row by -7, or I could say I'm multiplying it by a -1/7. Either way, so my top row does not change. My bottom row, however, 0 divided by -7 is still 0. -7 divided by -7 is 1. 35 divided by -7 is -5. This is now in row echelon form. What does it mean? Well, remember, this row here was the x coefficients, or this column here was the x coefficients. This column here was the y coefficients. This column here after the augmentation was the constants. So what this bottom row is telling us is that y equals -5. We went from the system of equations into the matrix. We can now go from the matrix back into a system of equations. What this top row is telling us was over here, the 1 is just 1x, -3 is -3y equals 17. Well, we found out the bottom row told us that y is -5, so we can substitute in x minus 3 times -5 equals 17. And then solve for x. Negative 3 times negative 5 is positive 15 equals 17. And we can subtract 15. So x equals 2. So we have x equals 2, y equals negative 5 is a solution to that system of equations. Now, that was just a two-variable system, and as you saw, there wasn't a lot of row operations. There's a lot of messing around to do there. Once we get into three variables, it can be even more tedious. So let's actually take a look at a system of equations in three variables and try to solve it. So we have 2x plus 2y plus 7z equals negative 1. 2x plus y plus 2z equals 2. 4x plus 6y plus z equals 15. So we need to create our matrix. It's going to be an augmented matrix. So we've got 2, 2, 7, and negative 1. So 2, 2, 7, negative 1. 2, 1, 2, and 2. 4, 6, 1, and 15. So we already have 1s here and here, but we don't know if we're going to be able to keep them there. We need to get a 1 here, and we need to get 0s in these locations. So what I'm going to do here is I'm going to multiply this middle row by a negative 2. So what that means, I'm going to write it off to the side over here. My top row is still 2, 2, 7, negative 1. That middle row becomes negative 4, negative 2, negative 4, negative 4. Multiplied every term by the negative 2. The bottom row is still 4, 6, 1, and 15. So what I want to do now for the next step is I want to add these two rows and use it to replace the bottom row. So my top row stays the same, 2, 2, 7, oops, getting a little crunch there, 2, 2, 7, negative 1. My middle row, I'm going to go back to what it was before I multiplied here, 2, 1, 2, and 2. The bottom row, I'm going to combine these. Negative 4 and 4 makes 0. Negative 2 and 6 makes 4. Negative 4 and 1 makes negative 3. And negative 4 and 15 makes 11. So I've got a 0 there. I need to get zeros in each of these two spots. So now I'm going to multiply that middle row again. Actually, you know what? I'm going to multiply the top row. I'm going to multiply it by negative 1 this time. So that's going to give me in that top row negative 2, negative 2, negative 7, and positive 1. Everything else is going to stay the same. Now you'll notice what I've done here is I got a 0 here in this row. What I'm attempting to do now is get a 0 here in the second row. Because once I get a 0 in that spot, then I can work on getting rid of this one. But really, until I have two rows where I have a 0 in the same spot, I really can't work on getting a second 0. Because whenever I try to 0 one out, the other number is going to add up, and that one won't be 0 anymore. So what I'm going to do here is I'm going to combine these two rows and replace the second row with them. So the top row, I'm going to go back to what I had before I multiplied again up here. 2, 2, 7, and negative 1. The middle row, negative 2 plus 2 is 0. Negative 2 plus 1 is negative 1. Negative 7 plus 2 is negative 5. And 1 plus 2 is 3. The bottom row has not changed. So now I've got zeros in both of these spots. So now I can use those two equations to try to get a 0 here. So what I'm going to do is I'm going to take this middle row times 4. So my top row doesn't change. That middle row times 4, well, 0 times 4 is still 0. Negative 1 times 4 is negative 4. Negative 5 times 4 is negative 20. And 3 times 4 is 12. My bottom row doesn't change. So now I'm going to combine these two rows, and I'm going to replace the bottom row with it. So my top row hasn't changed. My middle row, I'm going to go back to what it was before I multiplied it by 4. So I'm going to divide that by 4 if you want to get back to that 0, negative 1, negative 5, and 3. My bottom row, well, 0 plus 0 is 0. Negative 4 plus 4 is 0. Negative 20 plus negative 3 is negative 23. 12 plus 11 is 23. So now I'm almost there. What I'm going to do, I'm going to divide this top row by 2, which will give me 1, 1, 3.5, and negative 1/2. I'm going to multiply, so I was dividing that by 2. I'm going to multiply this second row by negative 1. So that's going to be 0, 1, 5, negative 3. This bottom row, I'm going to divide by a negative 23. So 0, 0, 1, and negative 1. So now I can translate this matrix back into a system of equations. This top matrix here is telling me that x, or top row of the matrix is telling me x plus y plus 3.5z equals a negative 1/2. The second row is telling me that y plus 5z equals negative 3. And the bottom row is telling me that x equals negative 1. Or sorry, not x, z equals negative 1, I should say. So then I can just substitute back into each equation. It's called back substitution. So I can put this negative 1 for z into the second equation. Y plus 5 times negative 1 equals negative 3. If I solve that, 5 times negative 1 is a negative 5, so I add 5 to both sides to get y equals 2. Then I use both of those in the top row, the top equation. X plus, well, y equals 2, plus 3.5 z, well, z is negative 1, equals negative 1/2. So 3.5 times negative 1 is negative 3.5, plus 2 is negative 1.5. If I add 1.5 to both sides, I get that x equals 1. So x is 1, y is 2, z is negative 1. That's the solution to that system of equations. Now, if I get to this point and I'm not sure of myself, and I'll be honest, when I'm using the matrices, I'm not as sure of myself as I am when I'm using just plain elimination or substitution. But let's go back up to that original system and check that solution, see if it works. We had 1, 2, -1. If I put in 1 there, that's a 2. Put in 2 there, that's a 4. Put in a -1 there, that's a -7. 2 plus 4 is 6, minus 7 is -1. The first equation is true. Let's test the other one. Put 1 in there, that gives me 2 times 1 is 2. Well, 2 there is just 2. 2 times -1, that's a -2. 2 plus 2 is 4, plus -2 is 2. Works in the second equation. Let's test the third equation. So if I put in 1 for x, 4 times 1 is 4. I put in 2 for y, 6 times 2 is 12. And I put in -1 for z. 4 plus 12 is 16, plus -1 is 15. So it does work in all three equations. That is our solution to that system of equations. Now you can see there are a lot of steps and there's a lot of matrices to write out. By no means is it a simple process. What we just did there is called Gaussian elimination with back substitution. Now we could keep going from this matrix here. We could have kept going and we could have avoided having to do the back substitution. So 1, 1, 3.5, -1/2. 0, 1, 5, -3. 0, 0, 1, -1. I could have continued from this and got zeros in these other locations away from my diagonal. Let's take a look at how that would work out. So in order to try to accomplish that, I'm going to multiply this equation here by a -1. So the top has not changed. 1, 1, 3.5, -1/2. The second equation is going to become 0, -1, -5, and 3. Bottom line has not changed at all. So now what I'm going to do is I'm going to add these top two lines and replace the top row with it. So 1 plus 0 is still 1. 1 plus -1 is 0. 3.5 plus -5 is a -1.5. 1/2 plus 3 is 2.5. The second row, I'm going to put it back to what it was before I multiplied by the negative. Back to this. 0, 1, 5, -3. And my bottom row has not been altered yet. So I'm going to continue to pick away at that top equation. To get rid of that -1/2, I'm going to multiply this row, or that -1.5. I'm going to multiply this bottom row by 1.5. So my top row is still the same. Middle row is still the same. That bottom row becomes 0, 0, 1.5, -1.5. Now what I'm going to do is I'm going to combine the top row with that bottom row. I'm going to replace the top row. So 1 plus 0 is still 1. 0 plus 0 is still 0. -1.5 plus 1.5 is also 0. 2.5 plus -1, yeah, that was -1.5. I wrote it wrong. 2.5 plus -1.5 is +1. My middle row is not changed. 0, 1, 5, negative 3. My bottom row, I'm going to go back to what it was before I multiplied it. So 0, 0, 1, negative 1. So the top row is accomplished. I have all zeros after the 1. All that's left to do is to make that 5 into a 0. To do that, I'm going to use the bottom equation. I have a 1 there. I'm going to multiply that bottom equation by a negative 5. So my top row does not change. My middle row does not change at this point. That bottom row becomes 0, 0, negative 5, positive 5. And now I'm going to combine the bottom two rows and replace the middle row. So my top row, 1, 0, 0, 1, stays the same. My middle row, 0 plus 0 is still 0. 1 plus 0 is still 1. 5 plus negative 5 is 0. Negative 3 plus 5 is 2. And for my bottom row, I'm going to go back to what I had before, 0, 0, 1, negative 1. You can see what I've done here now. If I translate this back into a system of equations, this top row is just saying x equals 1. The second row is just saying y equals 2. And the bottom row is simply saying z equals negative 1. There's no need for back substitution now. It's already completely solved. I get the same solution. In order to do this, I still had to use the Gaussian elimination to get zeros in these locations. It was a man by the name of Jordan that came up with the idea of getting zeros here. So that process is referred to as Gaussian-Jordan elimination. I realize I've gone a couple minutes past our break, so let's go ahead and take our break here. It's about 10:24, so let's go to about 10:32, 10:33, and we'll pick up from there. We'll do another example or two, and we'll talk a little bit more about these. Okay, so now we got everybody logged back in. Let's go ahead and do another example of the Gaussian-Jordan elimination here. So I'm going to stick with 3 variables here for now. You know what? Let's go with 4 variables. Why not? We got 2w plus y minus 3z equals 8. Notice I left a hole here. That's where the x would go in there, but there is an x in that equation. I've got w minus x plus 4z equals negative 10. 3w plus 5 minus y minus z equals 20. And w plus x, so I forgot my x, minus y minus z equals 6. So let's create our augmented matrix to represent this equation. Excuse me. So the top row will be 2. There's no x here, so we have to put in a 0 there. It's a 1y, so just 1, negative 3, and 8. Got 1, negative 1. There's no y, so it's a 0, 4, and negative 10. 3, 5, negative 1, negative 1, and 20. 1, 1, negative 1, negative 1, and 6. So for this one, we see that it might be rather simple to eliminate everything in this row except for this variable. Because that's a positive one, these are negative ones, I can eliminate those. So let's go ahead and do that. So what I'm going to do is I'm going to combine these two rows, and I'm going to replace the third row with them. So the top row stays 2, 0, 1, negative 3, and 8. The second row doesn't change. I got 1, negative 1, 0, 4, and negative 10. The third row, though, is going to be the combination of the first and the third. So 2 plus 3 is 5. 0 plus 5 is 5. 1 plus negative 1 is 0. Negative 3 plus negative 1 is a negative 4. And I have 8 plus 20 is 28. My bottom row is still 1, 1, negative 1, negative 1, 6. So in my next step, I'm going to combine the first row and the last row, and I'm going to replace the last row with it. So my first row stays the same, 2, 0, 1, negative 3, 8. Second row stays the same, 1, negative 1, 0, 4, negative 1. Second row, 5, 5, 0, negative 4, 28. Bottom row, though, is going to become 2 plus 1 is 3. 0 plus 1 is still 1. 1 plus negative 1 is 0. Negative 3 plus negative 1 is negative 4. And 8 plus 6 is 14. So now I have zeros in all of those positions. Now I actually want a 1 here, so what I'm going to do in this next step is I'm just going to exchange two rows. I'm going to exchange the top row and the third row. So the top row will now be 5, 5, 0, negative 4, 28. The second row is going to stay the same. The third row is now going to be the top row. 2, 0, 1, negative 3, and 8. And the bottom row stays the same. 3, 1, 0, negative 4, and 14. So we have a 1 here. That's part of what we want. We also have zeros here and here, which means we're getting closer. Now I'm going to work on this bottom row, trying to make these two equal 0. I'm going to start off by using this second row. I'm going to combine the second row and the bottom row, and I'm going to replace the bottom row with it. So the top row is still 5, 5, 0, negative 4, 28. My second row doesn't change. I'm using the second row, but I'm not replacing it. Third row doesn't change. My bottom row now becomes the combination of the second and the bottom row. 1 plus 3 is 4. Negative 1 plus 1 is 0. That's why I combined those two, is so I could get a 0 in that location. I use the second row because a 0 and a 0 keeps that location as 0 as well. 4 plus negative 4 is a 0. I get a bonus there. That cancels out. Negative 1 plus 14 is a 13. I'm going to exchange rows again. I'm going to put this row on top, and we'll put the top row on bottom. And in the process of doing that, I'm going to divide this row by 4. So that gives me 1, 0, 0, 0, 3 and a fourth. My second row, 1, negative 1, 0, 4, negative 1. Third row is still 2, 0, 1, negative 3, 8. My bottom row is now my old top row, 5, 5, 0, negative 4, 28. Should put my brackets on here. This top row is now complete. I don't need to do anything more with that. I've got a 1 there and all zeros. But it now becomes very useful for combining with my other rows. First thing I am going to do here is I am going to combine rows 2 and 4, and I'm going to replace row 2 with it. So my top row, 1, 0, 0, 0, 3 1/4. Second row is going to get replaced. 1 plus 5 is 6. Negative 1 plus 5 is 4. 0 plus 0 keeps a 0 there. 4 and negative 4 makes 0. Negative 1 and 28 makes 27. And my third and fourth rows are going to stay the same. Notice I now have all zeros here. I just need a 0 there. So I'm going to take my top row times negative 6. So I get negative 6, 0, 0, 0. So 3 1/4 times negative 6 is negative 19 1/2, I believe. Second row, we're not going to change right now. Third and fourth rows, we're going to leave alone at this moment. And now I'm going to add the first 2 rows, and I'm going to use it to replace that second row. Now my top row, I'm going to go back to what it was before I multiplied by 6. 1, 0, 0, 0, 3 1/4. I only multiplied by the 6 so that I could use it with the second row here. Negative 6 and 6 make 0. 0 and 4 is 4. 0 and 0 is 0 for both of those. Negative 19 1/2 and 27 is a 7 1/2. Bottom 2 rows are going to stay the same. 2, 0, 1, negative 3, 8. 5, 5, 0, negative 4, 28. Now that second row, I am going to divide by 4. So the top row is 1, 0, 0, 0, 3 1/4. That second row, dividing by 4, so 0, 4 divided by 4 is 1. 0, 0, 7 1/2 divided by 4. That is 15 over 2 times 1/4. Divided by 4 and multiplying by 1/4 are the same. Gives me 15 over 8, or 1 and 7/8. Oops, my numbers disappeared here. So that's 1 and 7/8. Notice that row is now complete. My bottom rows are going to stay as they were. So now I need to get zeros here, here, and here. And while we're at it, we'll get that one zeroed out too. So let's work on this one right here. To get rid of that, I'm going to multiply this top equation. Should put my brackets up here. I get a little sloppy with my brackets as I'm working just because it saves time not to write them in, but I really should write them in. So this top equation here is going to be multiplied by negative 2. Yeah, multiplied by negative 2. So I've got negative 2, 0, 0, 0, negative 6 1/2. The rest of my rows don't change at this point. So now I'm going to combine rows 1 and 3 and replace row 3 with them. So my top row, I'm going to go back to what it was before I multiplied. So 1, 0, 0, 0, 3 1/4. Second row doesn't change. That third row, I'm going to multiply it with or add it to the first row. -2 plus 2 is 0. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus -3 is -3. -6.5 plus 8 is 1.5. Bottom row isn't going to change. Well, let's work on that bottom row. Let's start by getting rid of this 5. So I'm going to multiply the top equation. Notice that's the one that has a 1 only in that location. It's all other zeros. So that I know I can use that to get rid of this 5 and not affect any of those other terms. So I'm going to multiply this by a -5. So I have -5, 0, 0, 0, -16 1/4. Other rows aren't going to change. And now I'm going to add that top row to the bottom row and replace the bottom row. Top row, I'm going to put it back to what it was before I multiplied it. Second and third row don't change. Bottom row is going to become -5 plus 5 is 0. The rest of that top row is zeros, so 5, 0, -4. In the augmentation, -16 1/4 and 28 is 11 3/4. Well, now let's get rid of this 5 here. So I'm going to use the second row because that's got a 1 in that second column and zeros everywhere else. So I'm going to multiply this second row by -5 and use it to get rid of that 5. So my top row stays 1, 0, 0, 0, 3 1/4. Second row becomes 0, -5, 0, 0. Let's see, 15 over 8 times -5 is -75 over 8. That's -9 3/8. And my third and fourth rows don't change at this moment. So then we're going to combine second and fourth row and replace the fourth row. So top row, 1, 0, 0, 0, 3 1/4. Second row, we're going to go back to what it was before we multiplied. 0, 1, 0, 0, 1 7/8. Third row, it hasn't changed. The last row, we're going to add it with that second row. So 0 and 0 is still 0. -5 and +5 is 0. 0 and 0 is 0. 0 and -4 is -4. 9 3/8 and 11 3/4 is 2 3/8. Now that bottom row has zeros in every spot. This needs to be a 1. So I'm going to divide that bottom row by -4. So everything else is going to stay the same. 1, 0, 0, 0, 3 1/4. 0, 1, 0, 0, 1 7/8. 0, 0, 1, -3, 1 1/2. That bottom row becomes 0, 0, 0, 1. That 2 3/8 divided by a -4. That's 16 19/8 times -1/4. That's -19 over 32. So now all we have left to do is to get a 0 in this location. To do that, I'm going to multiply that bottom row by a -3. I've got 1, 0, 0, 0, 3 1/4, 0, 1, 0, 0, 1 7/8, 0, 0, 1, -3, 1 1/2. That bottom row times negative, actually should be times -3, should be times a +3. Sorry about that. Times a +3. 0, 0, 0, 3. Negative 19 30-seconds times 3 is negative 57 30-seconds. So that's -1 and 25 30-seconds. So now we combine those bottom two rows and replace the bottom row. Or no, not the bottom row, we're going to replace the third row. So I got 1, 0, 0, 0, 3 1/4, 0, 1, 0, 0, 1 7/8, 0, 0, 0 plus 0 is 0, and 0 plus 0 is 0. 1 plus 0 is still 1. -3 plus 3 is 0. 1 1/2 plus a negative 25 30-seconds is a -9 30-seconds. Then put the bottom back to what it was before. 0, 0, 0, 1, -19 30-seconds. That is a lot of numbers, a lot of rewriting numbers. Notice even I had to be careful. I rewrote a couple of them incorrectly at times. But what this is telling me, this is W position. W equals 3 1/4. This is the X position. X equals 1 7/8. This is the Y position. Y equals -9 30-seconds. And the Z position. Z equals -19 30-seconds. Why is this? Of course, this was a Gaussian Jordan elimination because I didn't do back substitution. I eliminated all these to get them zeros as well. Throughout this process, you may have saw spots where you'd have done it differently, and that is just fine. The one thing with this Gaussian Jordan elimination with matrices is there are thousands of different combinations of things you can do to eliminate variables. One thing that had occurred to me at the time, we had the 5s across the bottom, and we had 1s in one of our other rows. Could have done this row times 5 and combined it with the bottom row, and it would have got rid of a lot of our stuff. So there's a lot of different routes you could take to make this, to get this matrix into the form we want it. The reason Gaussian Jordan elimination is useful to us in any form is because of the electronic factor. The graphing calculator can't do, well, unless you spend the money to get like a TI-96. For the most part, calculators don't work with variables. But I can look at this system here and I can create a matrix. So on a graphing calculator, if you have the TI-83 or TI-84, you can go into the matrix menu and you go over to edit and just select one of them. I'll select matrix A. The dimensions here, there is 1, 2, 3, 4 rows, and there are 5 columns. I count that augmentation as a column. So this is going to be a 4 by 5. And I'm just going to enter it. 2, 0, 1, -3, and 8. There's my first equation entered in. I've got 1, -1, 0, 4, -10. There's my second equation. 3, 5, -1, -1, and 20. 1, 1, -1, -1, and 6. I've entered my matrices. I exit out of there. I go back into my matrix menu, and I'm going to select math. In the math, I'm going to arrow down to RREF, reduced row echelon form. you'll notice that there is an REF. That's just a row echelon form. Remember, that would do the Gaussian elimination, and we'd have to back substitute. So RREF, I got to go in my matrix menu again and select matrix A. That's the one I put it in. Close my parentheses. It equals, it spits out this matrix. Now this is telling me I did something wrong in my calculations, because this is giving me nice, neat little numbers saying W is 1, X is 3, Y is 0, and Z is -2. I didn't think my numbers should have come out as ugly as they did. So somewhere along the lines, I had a miscalculation in those matrices. I'll be quite frank with you, the matrix calculations like this are not my favorite way of approaching systems of equations. When you get up into 4 variables, however, trying to do substitution or elimination is really quite painful. Remember when we had 3 variables and 3 equations, our first step was to eliminate it to 2 variables and 2 equations. Then we used those to get it down to 1 variable and 1 equation. 1 variable and 1 equation is what we're able to solve. We could solve that, and then we had to substitute back into the other equations to find the other variables. Well, when we have 4 variables and 4 equations, our first step would be to eliminate 1 variable, which would get us to 3 variables and 3 equations. Now there's 4 equations, so we'd actually have to eliminate it in 3 different equations. We'd have to go through 3 separate substitutions or 3 separate rounds of addition and elimination. And then we start the process of solving that 3 variable system. So reducing it to the 2 variables, then to 1, and then solving and back substituting. So with 4 variables, trying to solve it using substitution or the addition elimination method, it is very, very time consuming. You do need to be very careful because, as you noticed, I didn't get mine to solve out correctly either on the first shot there. So let's take a look at another system of equations here. We're going to go back down to 3 variables, just because we're a little short on time here. So we got 2x minus 4y plus z equals 3. X minus 3y plus z equals 5. 3x minus 7y plus 2z equals 12. Now, I'm going to warn you, something is going to happen. We are not actually going to be able to solve this system. Something is going to happen here. Well, we don't know for sure. Something might happen here. Remember when we were solving systems of equations before? We had dependent and inconsistent systems. In inconsistent systems, they were basically parallel lines. They had no solutions. When we went to solve the equations, they gave us something that just couldn't happen, like 7 equals 4 or something like that. There was no solution to them. Independent, we ended up finding that the two of the lines were the same lines. So all the points on either one of the lines were a solution to the system because they were the same lines. Well, if we're doing matrices, we don't get that luxury of having the variables disappear on us. What happens in matrices, if one of these 2 cases is present, is that a whole row will become zeros. So if that happens, then we have to go back and determine, is that a dependent system or is it an inconsistent system? with 3 variables and 3 equations, by the way, it's generally inconsistent. So anyway, let's put this into a matrix. So we've got 2, -4, 1, and 3, 1, -3, 1, and 5, 3, -7, 2, and 12. And let's go ahead and start trying to do our elimination. So what I'm going to try to do is I'm going to try to use this second equation here to eliminate this piece in both of the other ones. So I'm going to multiply this by a -1 first. So my top equation stays the same, or top line, I should say, stays the same. Second line becomes -1, +3, -1, -5. Bottom row stays the same. And now I'm going to combine the top 2 rows, replacing the top row. So 2 and -1 is 1. -4 and 3 is a -1. 1 and -1 is 0. 3 and -5 is -2. That second row, I'm going to put it back to what it was before. 1, -3, 2, and 5. And the bottom row hasn't been touched yet. So I've got a 0 there. Oops, this should be a 1 here in my second row. Now I'm going to try to get rid of the 2 in this bottom row right here. So I'm going to take my second row times -2. Top row doesn't change. Second row becomes -2, 6, -2, and -10. 3, -7, 2, and 12. Now I'm going to combine rows 2 and 3 and replace the third row. So 1, -1, 0, -2. That second row, I'm going to put it back to what it was before I multiplied it again. 1, -3, 1, and 5. Bottom row, -2 and 3 is 1. 6 and -7 is -1. -2 and 2 is 0. -10 and 12 is 2. Now there's something that's developed here that is concerning, or could be concerning. The top row and the bottom row are the same, but there's a different constant over here. When this happens, I know that I have one of these cases. If I have 2 rows where the part, ignoring the augmentation, where all the entries in those rows are the same, that means this is either dependent or inconsistent. If these numbers over here were the same, it would be dependent, but they are different. This system of equations is inconsistent. There is no solution to this system of equations. Because what this is saying up here, the top row is saying x minus y equals -2. The bottom row is saying x minus y equals +2. Both of those can't be true. X minus y has to equal the same thing every time. It can't be equal to 2 different things. So this is an inconsistent system of equations. So what happens if we have a system that looks like this? W plus 2x plus 3y minus z equals 7. 2x minus 3y plus z equals 4. And w minus 4x plus y equals 3. You'll notice here we have 4 variables, w, x, y, and z. but only 3 equations. This means we cannot get numerical solutions. But what we can do is we can eliminate 2 of the variables, or at least 1 of the variables, and then we can solve in terms of what's remaining. So let's create the matrices here. 1, 2, 3, -1, augmented with a 7. 0, 2, -3, 1, augmented with a 4. 1, -4, 1, 0, augmented with a 3. And what I'm going to do is I'm going to add together the first 2 equations here. And I'm going to replace the top one with it. So I add those together. I've got 1, 2 plus 2 is 4, 3 plus -3 is 0, 1 plus -1 is also 0, 7 plus 4 is 11. So now then I can, well, let's do, trying to figure out what I can get rid of here. I am going to use the top equation here, combine it with the bottom equation. I'm going to replace it in the bottom. So I've got 1, 4, 0, 0, augmented with an 11. 0, 2, -3, 1, 4. On bottom, I'm going to get 2, 0. 1 and 1 is 2. 4 and -4 is 0. 0 and 1 is 1. I got 0. 11 and 3 is 14. Right now I have a lot of zeros, but I don't have any variables that have like totally disappeared on me. Let's just put this back in the system of equations and see what we have right now. So up top here we have x plus 4y equals 11. 2y minus 3z, 2x, I should say. Let me reword that. I got that top one wrong. This is 4 variables. This is w plus 4x equals 11. The bottom one is 2x, or second one is 2x minus 3y plus z equals 4. And the bottom one is 2w plus y equals 14. The reason I wrote these out, because now I can solve them very easily. There's a couple of them I can solve. I can solve the top one for w, I can solve the bottom one for y. It really doesn't matter which. I'm going to go ahead and solve the top one for w. So I solve that top one for w. I get w equals 11 minus 4z. I'm going to substitute that into the bottom one down here. Set it away. So this bottom equation is going to become 2, out of my way here. There. So that's going to become 2, but instead of w, I'll put 11 minus 4z in it, plus y equals 14. So that's going to give me 22 minus 8z plus y equals 14. So what we have here, we have 2 equations. We have this one, 2x minus 3y plus z equals 4. This one, I'm going to subtract the 22 from both sides and rearrange. I've got y minus 8z equals -8. I can solve this bottom equation in terms of y. Y equals -8 plus 8z, and substitute that into the second equation. So this is going to give us 2x. Negative 3 times negative 8 is a positive 24. Negative 3 times 8z is negative 24z. Plus z equals 4. Combining, we got the 2x. I'm going to subtract 24 from both sides. Negative 24 and positive 1z is negative 23z. 4 minus 24 is negative 20. So I can solve that one for x if I want to by subtracting 23z. 2x equals negative 20 minus 23z and dividing by 2. Giving me x equals negative 10 minus 11.5z. So we've got x equals negative 10 minus 11.5z. Up above here, we had y equals negative 8 plus 8z. And then up above yet, we had that w is 11 minus 4z. That should be 11 minus 4x. That probably threw off the rest of my equations. But anyway, what we end up with is, you see, we have the equations where we have each variable defined in terms of only one other variable. So here, once we find z, we could find y and x. Once we find x, we could use it to find w. So we can't always reduce it down to just a numerical solution. Often, we can only reduce it down so that we have variables in terms of other variables, so that once we know one of the values, it's very quick to substitute them back in. Okay, we're going to call her a day because for some reason I'm having a lot of calculation issues today. I apologize for that. I've had a couple of bad calculation errors. Remember, there is an old homework from last Wednesday that is due tomorrow, due Tuesday. There's a new homework from today. It'll be due Thursday. Then there's going to be a quiz on the stuff from Wednesday and today that'll be due this Friday. So now this wraps up week 9 today. Wednesday will be the first day of week 10. So we'll have a lecture on Wednesday. Next Monday, November 11th, is test 2, midterm exam 2. So make sure we're ready for that. If we have time tomorrow, and there's no guarantee that we'll get time tomorrow to do it, but if we have time, I'll take the last few minutes to at least list out all the topics that you need to expect to see on that test. Anybody have any questions? Okay, hopefully by Wednesday, my internal calculator is back working a little bit better again, and we won't have so many problems. You guys have a great day, and we'll see you on Wednesday.